I'm Sam Kachuk, a postdoc in the Ice Dynamics group at the University of Michigan. First, I'd like to acknowledge my collaborators, Dan Martin, Jeremy Bassis, and Steve Price, whose support for this work was invaluable. In this talk, we're going to take a look beneath the ice, and I mean deep beneath the ice, to the mantle, and what it does in response to all the ice moving around on the Earth's surface, and then what that movement can mean for the ice's flow. We'll see that it can affect our forecasts of ice mass loss and sea level change, even on the relatively short timescales of decades and centuries. I want to convince you that you can be including solid Earth deformations without overwhelming your computations, and that you should be aware of the timescales and geographic regions where solid Earth deformations might be significant, such as around the Amundsen Sea embayment that we'll be focusing on here. The idea of solid Earth deformation driven by cryospheric changes, sometimes called glacial isostatic adjustment, might not sit comfortably with everyone, so let me briefly explain. If you apply a stress to the surface of the Earth, like a large block of ice, a few things happen pretty quickly. The mass of the ice changes the geoid, gravitationally attracting the oceans and increasing the load on coasts nearby the ice. The lithosphere and mantle compress and deflect elastically. The mantle is also hot enough that, given some more time, it deforms like a viscoelastic fluid. Mantle material flows away from under the mass, causing the surface to subside to get closer to the Earth's center of mass. Isostatic equilibrium is achieved when the mass of mantle material displaced equals the mass of the ice, with some caveats for the elastic support of the lithosphere. When the ice melts, the process reverses. The uplift or subsidence of the surface could have profound effects on the ice flow, particularly for marine terminating glaciers. The flow of marine-based ice through the grounding line depends on the thickness of the ice there. So if the bedrock deepens upstream, as it does at Pine Island and Thwaites glaciers, and something drives the grounding line back, it drives to a place where outflow is greater, which drives the grounding line back further still, in a positive feedback called the marine ice sheet instability. Solid Earth responses that lower sea level at the grounding line, either gravitationally or through uplift, could slow or even reverse the instability. We're pretty used to this viscoelastic deformation being significant for ice dynamics over long timescales, and consider it for the very large ice sheets, Laurentia, Fennoscandia, Greenland, focusing instead on the short-term dynamical effects of elastic uplift and gravitational attraction. The upper mantle has an average viscosity of 10 to the 21 Pascal seconds. For scale, water's viscosity at room temperature is 10 to the negative 3 Pascal seconds, and the tar in the 100-year-old pitch drop experiment is 10 to the 8 Pascal seconds, which has only dropped 9 drops to date. At 10 to the 21 Pascal seconds, the mantle can take tens of thousands of years to come to equilibrium after a continental scale load change. Thus, most ice modeling that has included viscoelastic GIA has treated it as a background process for contemporary and near-term ice modeling. The mantle is far from homogeneous, however, and observations indicate localized regions of much lower viscosity. Seismic studies show areas of very low wave velocities across West Antarctica, and GPS stations have recorded rapid uplift rates in parts of West Antarctica, both of which are associated with lower viscosities. Barletta et al.'s analysis of GPS stations around the Amundsen Sea embayment, which includes Pine Island and Thwaites glaciers, inferred an upper mantle viscosity on the order of 10 to the 18, 10 to the 19 Pascal seconds, and knocking 3 orders of magnitude off of the viscosities knocks 3 orders of magnitude off of the relaxation times. That long 10,000-year timescale that we're used to thinking about becomes a decade, commensurate with the retreat rate of Pine Island and Thwaites, and so possibly able to provide an important stabilizing feedback. We coupled the open-source Bicycles ice model to a viscoelastically deforming flat half-space, which includes purely elastic deformation, but not gravitational effects. The flat Earth model is convenient to capture a localized response because it depends only on fast Fourier transforms, using wavelength-dependent relaxation times for each time steps change in grounded ice. To establish a plausible upper bound, which will abbreviate UB on the magnitude of the viscoelastic feedback, we choose a viscosity of 10 to the 18 Pascal seconds with a 25-kilometer lithosphere, on the lower end of rheological inferences. As we'll see, the effect can be highly localized, so observations might be missing small areas of particularly low viscosity. For load changes on scales of an ice catchment, shown in this red bar along with our computational domain around Pine Island Glacier, the relaxation time is in the millennia for the upper mantle average, but in the decades for our UB rheology. The purely elastic lithosphere supports and accelerates the relaxation of shorter wavelength loads. So for ice mass changes about the size of the grounding line, which is where most of the action happens, shown in the left red bar, the response is subannual for the UB rheology. For ice changes with length scales greater than about 1,000 kilometers, though, shown in the gray bar, the flat Earth approximation begins to break down as the curvature and the self-gravitation of the Earth begin to matter. We'll watch the retreat of the Pine Island Glacier grounding line driven by parameterized ocean melt, focusing on the change in thickness above flotation, which is what drives both the viscoelastic response and sea level change. The plot on the top left has a static bed, and the one on the top right has a responsive mantle with our upper bound rheology. The initial topography is shown bottom left, and the solid Earth's vertical surface deformation for the responsive mantle is shown bottom right. As we begin to play it, note how the bulk of the action takes place around the grounding line, shown as black curves. Recall that the UB mantle rheology responds on subannual timescales for loads of this size. The grounding lines march back through the deepening valley, and up until 50 years the retreats are similar. After that, though, the uplift for larger wavelengths begin to catch up and to accumulate behind the grounding line, slowing the retreat. By 150 years, when the grounding line with the static bed approaches the domain boundary, the grounding line with the low viscosity upper mantle is 100 kilometers behind where it is without the solid Earth deformation. The rate is fast but highly localized, with velocities on the periphery on par with current observations, and central velocities easily missed by the present distribution of stations, shown here as stars. It's worth remembering that 90 meters is only about a third of the total 300 meters of uplift in isostatic equilibrium after the removal of a kilometer of ice. We summarize these results by integrating the thickness over flotation over the whole domain and plotting how much ice is lost in gigatons, or the equivalent sea level rise in millimeters over time. The sea level difference from including the response of a low viscosity mantle is 17 millimeters less over the 150-year simulation than the static bed. As a percentage of the sea level rise from retreat over a static bed, the responsive bed reduces the ice lost after 150 years by 30%. Given the uncertainties in the mantle's rheology, we can get a feel for how sensitive this is to a stiffer mantle rheology. With thicker lithospheres, which support more of the load change elastically and reduces the amount of viscoelastic uplift, we expect the negative feedback to be smaller. Indeed, increasing the lithospheric thickness from 25 kilometers to 60 kilometers reduces the sea level stability to 18% less ice lost after 150 years, still significant. Similarly, using the more viscous, layered best 2 rheology from the Barletta et al. Regional study with a 60-kilometer lithosphere, the longer relaxation times on top of the thicker lithosphere further decreases the magnitude of the feedback, so that after 150 years, the volume of ice lost is 12% less than a static bed. We can zoom out a little and consider what might happen for the entire Amundsen-C domain for IPCC projected forcings with low atmospheric change and mid to high ocean warming. We turn on the solid Earth feedback at 2010 and find again the solid Earth feedback on the sea level signal is on the order of 20% less than with a static bed by 2100. Bear in mind that this domain approaches the spatial scales where we will need to consider the shortcomings of the flat Earth approximation. To wrap up, glacial isostatic adjustment can proceed rapidly in areas with low viscosity upper mantles, in highly localized regions. Large heterogeneities make pinpointing these rheologies difficult, but the effect on sea level forecasts can be quite significant, over 10% for the best guessed regional rheology over century timescales. And though that might seem small compared to uncertainties associated with climate forcing and other parameters, it is computationally trivial to account for these near-field solid Earth effects, and better guesses for the rheology can be easily incorporated as they become available. Thank you very much for your time.